All right, hey everyone, what's up? Welcome to week 52 of Chill Kernel Hacking for Fun. Um, I want to thank you for watching, and this is pretty exciting. We are week 52 of weekly kernel streaming. So pretty much 1 full year of streaming kernel development every week. So yeah, it's pretty exciting for me. Thanks for being here, and we're going to keep it going today. I'm very excited to keep working on the file system lab today. So yes, that's what we're going to do. I'm just going to do my usual tests to make sure the chat plugin is working today. And we'll get going momentarily. Okay, test 0, not sure that's working. Maybe it'll take another few moments for the chat widget to come online. Yes, so today we are continuing with Lab 5. Last time we were starting Lab 5, we did the first few exercises. So the first exercise was to allow the user space file system server to have the permissions to do I/O, because in this design for this OS course, the driver is actually in user space, like that implements the file system. And actually this user space process directly talks to the disk using I/O instructions. And in order to do that, we need to give specifically this task privileges to do I/O. And apparently you can do this in eFlags. And so we worked on that. And then now we then started working a bit on the block cache. And there is this very interesting design where it actually makes use of our virtual memory and page faulting infrastructure that we previously worked on. We worked on some functions. So I need a moment to actually kind of remember how all of this works, but if I remember correctly, the general concept here is we are mapping a portion of the virtual address space of the file system server, and we're kind of using that as the block cache, basically. And so the way it works is that when there's a request for a disk block, that actually kind of arrives as a memory access. And if you want to access a certain sector or block from disk, you simply convert it to the appropriate page of memory, and you just access that memory. And behind the scenes, there's page fault handling in place. So if we haven't accessed this block from disk yet, we will have a page fault on that memory, and then our page fault handler will go and fetch the block from disk, populate it in memory, and then restart that memory access. And that's the way this block cache works, which is pretty interesting. And that's what we were working on last time. This is a pretty interesting design, but it has some limitations. Because we're on 32-bit, this means we can only handle disks up to the size of the virtual memory space available, which is kind of limited on 32-bit. Yeah. Hey Sam, thanks for joining. Hope you're doing well. Yo, what's up, John? Yo, thank you for the 1 year. Congrats. Yeah, that's kind of cool. Yeah, kind of crazy that it's been 1 year, but this stuff is just too much fun. So appreciate that. Yeah, today we are working on the file system lab and just kind of going through how it works. In general, it's a pretty interesting design where actually, so we basically kind of map the disk into memory, basically, but we do it in this kind of lazy way. So we reserve a portion of the virtual memory address space. When you access pages in that space, it actually faults in, it triggers a page fault, which will then read the contents actually from disk and then populate it in memory. So that's what we were working on last time. Yeah, and we're just gonna keep going with that. Yeah. Where the custom hoodie is, it's somewhere over here. It's like a little bit warm here today, but maybe I'll have to break that one out. Yeah. Yeah. How are you doing, John? Doing all right? Yeah. Okay. So I finished exercise 2 last time. And where is my terminal? Here it is. Drag this over here. So yeah, last time I was running the tests and it said we should pass these tests. Check BC, check super, check bitmap. Check BC, super bitmap, which we do. Got back from CCC a few days ago, actually. Crazy. So you were traveling for a bit, huh? That's pretty cool. Yeah, nice. Hope you had a good trip. All right, I'm going to kill this palm tree thing and restart it since we just started. Hey Sam, physical object. Right now it's all in emulation. So I'm just running it within QEMU. Yeah, I don't know. Eventually it would probably be cool to run it on hardware, but I don't have massive ambitions for that at the moment. Yeah, so just really, really simple, very vanilla stuff here. Let's get going. So fs init, let's take an example. Let's look at that as an example. Fs init is a prime example of how to use the block cache. After initializing the block cache, it stores pointers into the disk map region in the super global variable. After this point, we can simply read from the superstructure as if they were in memory, and our page fault handler will read them from disk as necessary. Let's take a look. I will clear out this stuff. Fs init. Why is it not finding this? Fs init. That is unfortunate. Okay. So yeah. Fs init initialize the file system. It has a static, which is interesting. I don't even know how you implement static assert in C. Apparently this is how you do it. Static assert, that struct size of file is 256. I guess this exact layout is quite important. Find the disk. Okay, I don't know. Block cache init. So yeah, what is this doing? We set our page fault handler. We have a local super variable cache the super block by reading it once. Okay, so this basically pages in the super block. Set super to point to the super block. Right, okay, so we initialize the block cache by which basically just means, yeah, we set up our page fault handler and just page in the super block, I guess. And then we actually set this so super is a pointer to disk adder. So this is a function that converts between block numbers and pointers within our virtual memory map of the disk. And apparently we have some consistency checks, like it can't be 0, and it also can't exceed the size of the disk. And otherwise we do a very simple conversion. And just as a reminder of how the disk layout works, the first block is reserved and unused. The file system starts from the second block, which has the super block. Going to make sure I have some of these, have some of these visuals here. And so, yeah, that's what we're doing here. We are accessing the first block to get access to the super block, which is just kind of like the header. And then apparently there's this bitmap thing, and that's where I start to really not know what's going on. And so there's a bitmap, which is just a pointer to an array of integers, which is interesting. Yeah. Can you link your diagramming tree? I can send you a link to this exercise. I'm not really sharing this, like, this is just kind of like my private development board. If you have any questions, I mean, maybe I could share it. It's just kind of like a lot of junk. I don't know if I have private stuff. I guess I probably don't. Yeah, it's just like private notes and like really random stuff. Yep. Honestly, I don't even understand half the stuff I put in here. Yes, so. Okay, some challenges. I'm not going to do the challenges right now. The block bitmap. After it sets the bitmap point, we can treat bitmap as a packed array of bits, one for each block on the disk. For example, block is free simply checks whether a given block is marked free in the bitmap. So I don't completely understand the purpose of the bitmap right now because I'm just learning about it right now, but presumably it's for keeping track of what is in use on the disk. Yeah, this is actually a personal project. I mean, it is a school project. It comes from this MIT course, but I am not a student. I'm not like enrolled in this course. I'm just doing it because it's some free learning materials and is pretty high quality. So, but I'm just doing it for fun. I'm not getting any school credit or something. Yeah, okay. So basically a bitmap is just, a compact structure. It's kind of like a hash map from integers to booleans. And it's just an optimized version of that data structure. And so the integers are like indices into the bitmap, and then we just store some bits for booleans. So apparently we want to check or like record which blocks are actually in use or not. Okay. Use free block as a model to implement alloc block which should find a free disk block in the bitmap, mark it used, and return the number of the block. When you allocate a block, you should immediately flush the changed bitmap block to disk with flush block to help file system consistency. Okay, so basically, as part of our, like, in order to make a file system, we're going to need to write data to disk, and we need to allocate memory. Like, disk is basically this big region, and we will need to find blocks of memory that are free to write our data to, just like a memory allocator, basically. And apparently here we're just using a bitmap to store which blocks are free, and I guess we're just going to linearly search through the bitmap to find a free block. And I guess we can do this because, like, unlike with a normal memory allocator, I don't know, well, maybe our actual memory allocator could work like this too. But we know up front the size of the disk, I suppose, or we can find that out. So yeah, so let's free block. Okay. So free block. So free block is the model to implement alloc block. And so this is basically the free function. We're given a block number and we want to free it, which means marking it as unused in whatever data structures we're using. For the normal memory allocator, we might unlink it from our linked list of blocks, but here we don't, I guess we don't have like metadata. We do, but I guess it's stored in a different place. So all it takes here is to set the bit to 0. And the way that works is we need to convert the block number into a bit index and then set that to 0. And so it obviously shows us how to do this. So we need to divide by 32 to get the byte index, basically. So like blocks 0 through 31 are all going to be stored in the 0th byte of the bitmap. So we divide by 32 to compute the byte. Yeah, it's like the byte location in the bitmap. And then what is this? This is actually kind of interesting. It seems like we're actually ORing in a 1 to mark it as free, which is a little bit unintuitive to me. But that's what this comment says also. Return 1 if a block is free, 0 if not. So that means at some point we need to set them all to 1 or something to make them all free, basically. Is that how this works actually? All reserved blocks 0 are marked as in use. Sure, all not block is free. Okay, I'm still not seeing the place where we set, so maybe this will show file free block. Interesting. Because like I'm assuming it's 0, or maybe when the file system is created, this is created in this state, and maybe that code is in a separate place. I'm not going to fixate on that too much right now. So we're trying to implement alloc block, so let's do that. Market used, return the number of the block. Find a free block, market used, return the number of the block, and flush it. Okay. Search the bitmap and allocate it. When you immediately flush it, return block number, return some error. Hint, use free block. Okay. The bitmap consists of one or more blocks. A single bitmap block contains the in-use bits. Okay, they are super blocks in the disk altogether. Okay, so what do we need to do? We need to, like, what's the dumbest way to solve this? I'm just gonna do it the dumbest way first and then make it smarter later. And blocks. Oh shit. Wait. Okay, let me try that one more time. And I equals 0 less than super s and blocks I plus plus. So the dumbest way to do this is we iterate through every single block index, and we check if it's free, basically. If block is free, I'm kind of surprised that we don't have a compiler warning because we're doing a type conversion. So if the block is free, then we alloc block and int ret equals 0, like set ret, return ret, fail, and then apparently return if we are out of blocks. So what how if we're out of blocks, what happens? So maybe I'll make this -1 as a, but actually, wait a sec. There's an unsigned 32-bit int as the block number type, but here we are returning a signed int, which means we cannot actually represent technically the full range of blocks. However, we're probably not going to use the full uint space because our disk is limited to 3 GB. Just for some quick stupid math, let's say so 3 times byte, that's 3 GB. And what's our block size again? Our block size is, why did I not write this down? Okay, block size is 4K, sector size is 512. We're searching for a block, though, which is 4K. So just out of curiosity, on a 3 GB disk, how many blocks are there? There's this number of blocks, 800,000 blocks. which is the max number of blocks we can support currently, which means that, so this number is lower than uint32t, which means we're not even using the full space. So this number is lower than than uint32t. It's also totally possible to represent this number in a signed int, which means we don't really have to worry about returning a super high block number that we can't represent with a signed int. So that's good. Just taking a moment to welcome, hey everyone, welcome if you're joining the stream. We got a lot of people in the stream today. I have no idea why there's so many people, but thanks for being here. We got 13 people in the stream right now. That is amazing. So thanks for coming to celebrate my 1 year streaming with me. Okay. I kind of wonder if I should make a static assert or something like this. I'm gonna leave a comment for now. Block numbers are uint32t. However, we return from this. Might be problematic since we can't represent all block numbers. In practice, we have a 3 gigabyte limit on the disk we can support. Which is blocks, which can be represented by both uint32t and int just fine. We might want to have an assert somewhere here. I don't know. The assert could, for example, be in functions that receive a block number. They could assert that the block number is within the allowed range. That's not really the case here, so. And we have hit our first break of the day. Also, what's up, Icron? Thank you, thank you. Let's all take a quick break for 15 seconds, stand up and stretch, get some water. Yes, okay. So back to this. So here's generally what we're doing. So actually, you know what? There's no reason. We can just directly return it, I think. We don't need to have this. So we can actually, I'm just going to turn block number. We don't need this. Flush to disk. And to alloc the block, what do? Well, we kind of already saw how to do it. And ideally, if we were good software engineers, we would probably make a function for this. Maybe I will do that. Bitmap set alloc block. I don't know. 32t block number const. Okay, weird. And so, I mean, bitmap is a global variable, a little bit unfortunate. I am going to try to not promote that behavior by making this take a bitmap. 32T bitmap, which is a bit unfortunate that it aliases the global bitmap symbol. Call it P bitmap. P bitmap. Right. So. But no, wait a sec. To mark it as, this is freeing it, so we want kind of the opposite. We want to basically set it as 0. So we want to, all right, I'm just going to hard code it here and then make the function later maybe. So we want to take this thing and forcibly insert a 0, which means we need to and equal something. And what are we and equaling? We want to make, we basically want to, for example, you know, let's say it's the first bit, you know, that produces this in binary, and we want to invert this. I think that didn't quite work out how I wanted, but I'm pretty sure, yeah. So we want to basically produce the bitmap, plot number, yeah. So we want to, also it's I. Also we could use a bit of spacing here, I think, to make this more legible. So we take I, it would be nice to just have a place to write some text. So, for example, let's just say it's with 4 bits or whatever, just to, so this is like some bits. So let's say we're trying to allocate the index 1 block. So we want to create a bit mask, looks like this, but eventually we want to and in a bit mask like byte. Also, I hope you can see, hope it's visible. My camera's not blocking this. So I'll move this a bit over. So this is just bit twiddling basics, but in order to clear a bit, we're gonna and everything with 1s except for the bit we want to clear. So this is the bit mask we want to produce. The way we get this is by first creating this, then inverting it like this. And that's what we are doing here, I believe. We are first producing this 1 positioned into the correct place, flipping that, and then anding it in. So I will P bitmap. Block, bitmap, and I. return I. I is the block number. And if it was saying we need to flush some stuff to disk. Hey, what's up, Larry? As someone who's pursuing a career in cybersecurity, watching this stream is making me want to give up. Yo, don't give up. That's not what I'm trying to show here. What I'm trying to show is that this stuff is not magic, and honestly, you know, some parts are difficult, but it's not like some crazy witchcraft. I'm like not particularly a genius programmer. You know, all I did here was make a for loop where I'm calling an if statement. You know, the bit, like, sure, the bit twiddling is a little bit esoteric if you're not used to that stuff, but I definitely do not want you to quit. And in fact, being like, yeah, cybersecurity is a great path if you want to eventually do this kind of stuff. What's up, Bishwaz? Nice to see you again. Do you know Terry Davis? Of course I know of Temple OS. I never like met Terry Davis, but yeah, I think that's a cool project, and his story is pretty unfortunate. But yeah, I would say that's also an inspiration of mine. Okay. And return the number of that block. When you allocate, you should immediately flush the changed with flush block. So how do we use flush block again? With the pointer. So we just pass the bitmap. So that's like pretty much it, y'all. That's how we're going to allocate a block of memory from the disk. We are going to iterate through the number of blocks. You know, we could even assert n blocks is sane. You know, there's a lot of things we could do. Yeah. So I will definitely be checking back in every once in a while on your progress. I also shared your live stream in the TPSC Discord. Awesome, appreciate that, Larry. Thanks a lot. What is the TPSC Discord? I've never heard of that. Yeah, appreciate that. I'm here every week. I've been doing this for a year. I'm not planning on stopping, so yeah. Also, what's up? Your name is in Japanese. I don't know how to read that. The best thing is I haven't seen you use LLM so far, unless you got a hidden tab open. I do use ChatGPT from time to time, but I'm explicitly trying not to. I am trying to just kind of raw dog this if I can, and just like type the code out and you know, go slow and stuff. PC security channel. Use AVs. Okay, cool. Yeah, I'm trying to not use LLMs if I can. Just kind of like just do it manually. As an exercise in coding, let's add an assert here. I think asserts are kind of interesting because I would call them a bit of a finer point of programming, because you don't really need them in your code, but they can be useful more in a long-term perspective if you're trying to maintain code. And the assert is going to be something like assert super sn blocks is less than like max blocks or something like that. You know, that's a bad name. I don't think we want to keep that name, but disk map. But we have some constants, disk, and define disk max blocks. Any plan after completing this project, like adding new stuff to it? So here's my overall plan. Is step one, learn how to do operating systems development. And that's what I'm doing right now, because I don't actually know. That's the whole reason. Like when I started a year ago, I was a total noob. I didn't really know, like not a total noob, but I didn't know like even the most basic things about OS development, really. So once I learn it, after completing this course, I will consider myself having like the knowledge of kind of how it works. From then on, I want to actually make my own OS, because I'm not doing that right now. And I want to make like a really weird and like funky OS. And yeah, write more of the code from scratch, do it a bit cleaner, and make something I can be proud of. So that's kind of my perspective. Yeah, I want to just do some weird stuff. I want to add like audio support, and maybe USB support would be cool. Those are things I'm personally interested in. So what was the best way to do this? So do we have any constants for like disk size or something like that? I don't think so. Here's what we're going to do. I feel like I should know this constant by heart or something, but here's one. So kilobyte, megabyte, gigabyte, hex. Maybe that's confusing. Maybe I'm just going to do this raw and say 3 or maybe disk max size is 3 gigabytes. Disk max size divided by block size. Page size divided by block size. And so now we have, before we go and do this whole thing, we have this assert now to do a bit of sanity testing. Audio and USB doesn++ sound like a coincidence. Yeah. I think you write in C as well. Probably not. Like, probably C++. Yeah. Yeah. I mean, if I'm being honest, I think I was pretty inspired by your OS also, John. Like the relatively super clean C++. Can make a lot of things nicer. So I'm kind of interested actually in doing a bit more of an object-oriented style OS and seeing what that looks like using object-oriented principles, and also making it testable, which you can do with object-oriented code quite nicely, because with object-oriented code you can use runtime polymorphism and interfaces, and like I don't know if it's a dumb idea to try to like mock stuff and make it more testable that way, but I'm kind of interested in these concepts. So yeah. What's up, Digitalized? Nice to see you. Oh, wait. Okay, I am being kind of dumb here. We already have a constant for disk size. So yeah. Yeah, dude, for anyone watching, John has like this crazy OS that's actually pretty awesome. And I would consider it it uses like really modern C++. I think it's targeting ARM systems right now. But yeah. Yes. So what's up? Not a typical name, not even Max, Emacs, or Vim. You're not hacking. Damn, man, I think you're right. I'm guilty as charged. Although I am using Vim key bindings, so that doesn't count. So we've asserted that n blocks is less than disk max blocks. And we iterate through every valid block number, check if it's free. There's probably ways to optimize this, but if it is free, we set it to not free by ORing in a 0 basically. We flush the block and return the block number. I think that is mostly it. So now I'm going to try to see if we pass this new test. What is it called? Alloc block. Okay, let's run these tests. Internal FS tests. All right. Okay, sick. We got OKs for all the tests. Yeah, for anyone interested in learning OS development, I also one reason you might want to follow these OS courses, like this OS course material that's online, is because it comes with the unit tests and it comes with a lot of testing, which you're not going to get if you're starting from scratch. And I've personally found it pretty helpful. What's up, Jan? Hey, stopping for the first time, you popped up on the recommended. No clue what you're working on, but it looks very interesting. Thank you for joining. I'm working on the file system for my OS, but more specifically, I'm working through these file system exercises as part of this course. So we did lab 3. Let's move on to lab 4. Yep, it's just a uni OS course. We have provided a variety of functions to implement the basic facilities you'll need to interpret and manage file structures, scan and manage the entries of directory files, and walk the file system from the root to resolve an absolute path name. Read through all the code and make sure you understand what each function does before proceeding. Okay. Let's make a commit first. So we'll get the big job soon. Young Buck, thank you. Appreciate the support. Do I need this comment? Okay, so actually our assert guarantees that we'll stay within the range of int. I am not really going to focus on this too much right now. I'm just going to size 3, implement free block. Okay, cool. So let's proceed. So, okay, it's telling us we need to read all the code in fs.c. Let's do that. So, how long is this file? It's like not that long. But before we continue, quick 20-second break, stand up, stretch, whatever. Wow, we got a lot of people in the chat today. That's pretty cool. I think that's a record for me, actually. I don't think I've ever had 24 people in the chat before. That is crazy. Well, welcome to anyone joining. Okay, so it's time to read this. So we have a couple of things here. We have some global variables. Not amazing, but that's what we have. We pointer to the super block, and bitmap pointer. What else? Check super. So we validate the super block we have the magic number there? Ah, okay, we already have this thing, disk size minus block size. So apparently we will already panic early if the block size, if we cannot support the block size, which is good. And then what block is free? We already looked at this. This just checks. Yeah, so when is a block free? A block free is, what are the requirements of that? So it can't be the first block, because that's reserved. It can't be past the number of blocks. And then, okay, then we have this kind of like weird if statement. This could all be reduced into a single line, but for some reason it's like if blah, return 1, also always return 0. Then the function I just added to allocate a block. Freeing a block is the opposite. We can't free the 0 block. We can free anything else by putting a 0 into the bitmap. I just wrote alloc block, check bitmap. Okay, whatever. File system init is what? Find a disk. Use the second IDE disk. Number 1, if available. If IDE probe disk 1. Interesting. I don't really know what that is doing, but maybe it's not so hard to understand. So it's like time to find a disk, I guess. So switch to device 1. Okay, I really am not sure how this works. This looks weird. So in general, the kernel is on disk 0 and our file system is on disk 1. Return x is less than 1,000. Okay, don't know what that is. And apparently, okay, so if disk 1 is available, we use it. Otherwise, I guess we use disk 0. And we call the set disk thing, which is apparently just sets a global variable for like which disk we're using. And it cannot, if, yeah, and it has to be either 0 or 1. We initialize the block cache, which we already looked at. We then just get pointers to the super block in the bitmap so this just computes a pointer. It doesn't actually do a memory access, and it doesn't actually page things in from disk. But we need to do the disk needs to be prepared before we do the block cache init, because as part of caching in, by reading the super block, we actually will need to read the disk using the page fault handler, actually. Okay, so, okay, then we have some functions which are kind of new. We have a function that file block walk, find the disk block number for the file B and block in file F. Set it. This is like pagedir walk for files. So we have a given file, and the file can be composed of multiple blocks, and those blocks can be all around the disk. And so we're just trying to look up the actual block number for a certain block of the file, like a certain chunk of the file, basically. Okay, file get block, set block to the address and memory where this certain block of the file would be mapped. So I think that's just a memory. Okay. Dir lookup. Try to find a file named name in dir. Try to find a file named name in dir. If so, set file to it. Okay, so we're like looking up a file within a directory. Given the struct file that corresponds to a directory and like a string name, we iterate the directory entries or something like that. Let's see, okay. Search dir for name. Maintain the invariant that the size of a directory file is always a multiple of the file system's block size. Okay. So what is, so the dir is a struct file. And what is a struct file again? So like how do directories work? This was explained in, this was explained a bit above here. Directories versus, yeah. The file structure can represent either a file or a directory. And these two types are distinguished by a field in the structure. And the way directories work is that the data blocks of a directory file are like a series of file structures. Interprets the contents as a series of file structures. So what we need to do basically is we're given a file, we need to read its contents by using file get block. And then once we have that data, we interpret it as struct files. And then for each of those, we need to look up its name, which is just in like the name field, basically. And so yeah, so first step, get the file size of the directory and convert that into a number of blocks. And then for every block, we read the block. Interesting file. So we haven't done this yet, but this function returns a pointer to the data. And then this is basically going to be an array of struct files. And so then, am I actually correct about that? I think yeah, this is an array. And these names are all single letters. So it's a little bit hard to see, but we're indexing into this F array. So for every, and there's a certain number of files in each block. And it seems like we are just iterating through all of them. Okay, I have some questions, but that'll come later. So we look up, maybe it is helpful to have this thing here. So basically, yeah. File we're like reading all the blocks. In each block, maybe I'll even draw it out to try to help clarify this. So what does this look like? So the starting point is we have a data structure. It's a struct file, but it's the directory. And conceptually, this file has like a bunch of data blocks, just like any file has data, except the unique thing about a directory is that the data of the directory is basically like metadata about files actually. And so we have, maybe I won't type it in here, so then within each block, actually I'll make this a little bit bigger. So we have these blocks. Let's say there's 2 blocks of data. Within each, so each of these blocks is 4K in size. The size of one of these structures is 256, so 4690. So that means there can be 16 files. So basically, this is, that's not what I meant. So within each of these blocks, we can basically have, you know, this is not to scale, this is only 8, but it's like 1 through index 15. And these are all struct files. Also. And within each of these things, we have this whole thing. So the basically way it works is, in order to look up a file within a directory, we're going to iterate through all of these blocks and basically check against the name field that's sitting in each one of these. And it potentially will go into, like, potentially there's many different 4K chunks, and we'll need to iterate through all of them. I'm kind of wondering how, like, let's say a directory only has 2 files in it. How do we know to stop at the second one? Is there any way to distinguish like an unallocated file here? Or not? Because it doesn't look like they're doing this. They're just like blindly iterating through all 16 of these and just hoping, I guess, that this is like 0 initialized or something. And maybe that's the case. Maybe that's just how it works. If it's like, it's all 0 initialized if there are no files in this directory. So anyway, if we found it, if we did a string compare against the name in it and it was valid, we return a pointer to the struct file and return. Okay. And so conversely, so for creating a file, that file to point at a free file structure in dir, the caller is responsible for filling in the fields. So we kind of want to do a very similar thing, except this time we are looking for a free slot here, basically. And interesting. So first thing we do is the directory, we see how big the directory is. Like how many, is it using 1 4K chunk? Is it already using 2 4K chunks? Like how big is it already? And within the bounds of its current scope, we just check if there is a free one available. So that's what we're just doing here. Same kind of loop. We get the full size, we convert it to the number of blocks, and then we just iterate through all those blocks. So remember this thing is a block. So each 4K chunk is a block. And so for every block, we iterate. So for every block, we get the block, which is what and then we iterate through one or I guess 0 through 15 in each one of these, and check. Okay, so this confirms it. If the name is an empty string, that means the block is not allocated. That's what that means. So we will check for the name being, like the first byte of the name being a null. In that case, it's free. And then, but what if it was perfectly filled up? Like what if every single one of these was used? Then we need to actually allocate another block to expand the directory, which is what we do here. We increment it by block size, which is the 4096 number. So this is the size in bytes. We then file get block. Yeah, which requires allocating a block. We then get this block and then set the file to the first file within that block. It looks like we have some helper functions here for skipping slashes. So you can give it a pointer and it will just advance it until it no longer points to a slash. That sounds kind of interesting. Useful walk path. This is an even higher level thing. Given a full path with slashes and stuff, I don't know, fully resolve it to the file that it points at, I guess. Okay, set to the file and the directory it's in. If we can't find the file, but find the directory, set Peter and copy the final path element into last. Interesting, that's kind of weird. Okay, how does this work? So this is like kind of long. So we're basically interpreting this path, and the path is text delimited by slashes, basically. So starting from the path, we skip slashes until we get to the actual first chunk of data, which we apparently reassign to path. Interesting, okay. And then for some reason we save a local pointer to the root directory, which is useful for some reason. And I guess we are just initializing some of the variables. If Peter if we were given a Peter, we set it to 0, apparently. Wait, what? Yeah, we set it to 0 for some reason. So I guess the way this function works is that it always zeroes it out and then maybe it populates it on success. All right, be right back. Okay, so we zero out the output parameter. We also zero out both of, it's funny, we don't even check if this is null, we just zero it out. So I guess, is Peter optional? It doesn't really say that it is, okay, whatever. Okay, then path. Is it just a simple DFS for the path? Probably. Well, I guess probably yes. the thing, like, the reason why I'm hesitating to call it a DFS is because usually with like DFS, my understanding is that you have this graph and you have an element, and you're like looking through the whole graph to try to find this element, and you have no other information about where the element lives in the graph. The difference here is that we don't just have the element to look for, we have the full path of the element. And so it's not quite a DFS, it's like pretty directed. It's like just locating the element within the graph, but we also know the exact path to basically find it. So it's more of like this, like a lookup. But yeah, but let's actually see. This is like, I don't know, hard to read, but so while path does not point to so while we didn't reach the end of the path, we have a million local variables here. We set directory. So directory contains kind of like the current cursor of where we are in the tree. And although actually, does F get reassigned? No, I hope not. So we set directory to the root, it looks like, because F is the root. P is set to path. Oh my, I hate reading C code like this. And while, but what, we also mutate path. While path doesn't point to a while path does not point to a slash and is not a null increment. So like, so we have like a path. I'm gonna just like home, offline, mark, kernel, dev, for example. And so we basically like, we have a couple of variables here, path, and path at the start points at the first data byte, which is like the O, and we have P. And P gets stashed to point at path, and then path gets incremented all the way until the first like invalid thing. So it points to one past the end of the last valid data byte. So these two kind of frame the like directory name basically. And then we subtract them to get the name of the length of the directory name. If it exceeds this thing, that's like not allowed. Otherwise, we copy it into a local buffer of a local buffer, which we null terminate. And then path, what happens to path? Path gets, so let's say there's a bunch of slashes here. So path originally points to the first one, then we like zoom it forward to point to the next thing. That's what this skip slash does. If dir f type is not equal to f, okay, it seems that's a kind of weird that we were doing this check so late. We should probably just do this earlier as soon as we have dir, but whatever. Okay, so if this dir thing is not even a directory, then we return not found. Otherwise, we try to look up this name within the directory. So basically, directory points to the data structure corresponding like to the parent, for example, which is kind of like, it's like the home. And then we extract the name, and then we look for this name within the directory. And if it's E not found and path equals 0, the path points to a null pointer. Okay, what? Hey, what's up, Kirby? Thank you for joining the chat. So yeah, so we will try to look up this thing within the directory, and then what? There's some strange conditions here. If it's less than 0, meaning if there was an error, I see. But if it succeeded, it'll write back into F, and we'll continue the loop, basically. Hey, Trauma. What's up? Weird question. How do you know what to do? Do you make up everything in your mind, or are there instructions on what a file system needs and how it approximately is done? That's a great question. I totally don't make it up. I am just following this course. So if you want to take a look, here's the link. But yeah, I am totally just robotically following this course for a year now. So I'm not making it up. Eventually it would be cool to kind of think about like a file system from the ground up or whatever, but that's not what I'm doing. So here then we look up the directory, and if it succeeds, it'll return like 0 and write the directory back into F, and then this thing will continue. If there was an error, then we just return. But apparently if there was like some specific error, like if it was not found and path points to a null pointer, like if you were at the end of the string, this corresponds to this part where it's like if we cannot find the file, but the directory, if we can't find the file but find the directory it should be in, set blah 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 blah. We can't find the file, so this means we couldn't find the file, but we found the directory. So we did find the directory clearly. So we didn't find the file, so we just set the Peter and last lm. Wonder why they use unsafe stir copy. Yeah, interesting question. If last lm, and so basically the caller can pass in a buffer and copy the final path into last lm. But yeah, that's a good observation. Like usually when you pass in a buffer, you also pass in a size, so the code can check if it's going to overflow that. That totally doesn't exist here. And so the caller needs to make sure to provide a buffer that is at least max name length long, otherwise it will overflow. So yeah, that is an accident waiting to happen, probably. Yeah, they just YOLO the buffer. I mean, that's like a lot of like this style of C programming. Like if you're not particularly rigorous about your C programming, yeah, you like do stuff like this. And you just kind of YOLO it and probably risk overflowing stuff later if someone didn't know how big they needed to create the buffer before passing it in, because it's not actually documented in this function signature. So you need to read this function to know that the minimum size required for this argument. What's up 2v2? Do you do any kernel driver fuzzers? Do Do you know of any kernel driver browsers? I don't. I'm not super like clued into that particular area. So yeah, I don't know too much about it. I know there's syscaller, which is for fuzzing the Linux kernel syscall interface, I think, but that's not for drivers. So I am not totally sure. Anyway, they have this like big function, and interestingly, so they have this code at the very end. So what happens if we just like reach the end of the string? If we just like completely safely reach the end of the string, then f will contain the file, the struct file that corresponds to the last element in this path, and so that's what we assign here. And then dir will contain the directory that it was in, and we just return a success code. So that's how you might walk a path and fully resolve a path into a like data structure. It's not exactly like this, but it's conceptually similar to resolving a virtual address into a pointer to a page table entry. Obviously, a virtual address is very different from a file path, but the kind of concept it's like this token that represents some object that's like stored in this data structure. And for a virtual address, it is like a packed set of numbers that tells you where to find this page table entry. And for a file path, it is a set of strings that are just packed together. But it's conceptually a very similar thing. A virtual address is kind of like a path through the page tables actually, and it's just numbers, and so we can represent it very efficiently with bits. It would be kind of a creative and weird idea. So what if we had a file system where you are only allowed to use numbers to name things and you can't use text? If we did that, then we could like pack it into like this really compact like int basically, and have it very much resemble a page table walk. Actually, that's like kind of a quirky idea. Would be pretty hard to use probably, but yeah. So anyway, moving on, file create. So now we're getting into like the high level API, I guess. So let's say we were trying to create a path. We just give it a path and an output parameter for the struct file if it's created. You are beautiful, my dude. Subbed. Yo, thank you, Cairo. Appreciate that. All my file names would be leet. Speak that number. Only leet speak. And then, hell yeah. Number. Who needs usability in their file system if it's cool? Yeah. Dude, that might be a good stunt hack. I've been looking for some good, like, stunts to pull. And the number only file system might be a good one. If for some reason, like, humans don't really need to interact with the file system, then yeah, make it number only, and you could have these super efficiently packed like paths, I guess. Maybe, I don't know. There's probably a lot of problems with that, but because you need to like delimit them somehow, and it would also kind of put max limits on your directory sizes, but those exist anyway. So yeah, if you have any other stunt hacking ideas, I would love to hear them. But yeah, that's that's what I'll be doing once I know enough about this stuff. I want to work on some cool like OS stunts, some really really wild and insane stuff. Okay, so we walk the path and get the file, and if it doesn't exist, we bail out. Otherwise, okay. So if that just failed, Ah, I see. So if we query for the path, and if it returns success, that means it already exists. So we're not going to create it. Otherwise, if it was not, so if we found it, if it was not found, so if we found it or the directory didn't exist, we return the error code. Otherwise, we allocate a file using that function we already saw. Asking ChatGPT, so don't quote me, but it said cloud providers like S3 and Google Cloud do something like that. Oh, neat. Did not know that. Okay. So then we allocate our file. So now we have the directory. We can allocate a file and get a pointer back out to it, and we kind of reuse this thing. If that failed, we bail out. Otherwise, we've finally allocated a file structure. And it's time to populate it. And the main way we do this is to copy in the name, because the name field is the key way it's differentiated whether a file is present or not. And so that's the key thing we need to populate. So we populate in the name, and this never gets zero initialized. So I hope this function, right? And this is exactly what digitalized what you were talking about earlier. So here we are looking at the client of walkpath, and we can see that they actually do pass an appropriately sized buffer. It's it's a max name length buffer. So there won't be a buffer overflow. The question is, how do we know that this buffer will be null terminated? And we know that because it's copied in from here, which is null terminated. But wait a sec, does stir copy the null terminator? Okay, I don't even. Okay, I don't. How? I'm pretty sure it does. Yeah, you're probably right. There are like, man, stir copy. The thing is, like, it's stir copy. Return value. All right. Quick 20-second break. Be right back. This actually copy the string pointing into a string at the buffer Sterling Cirrus +1. Including the terminating null byte, right? So that's correct. Yo, what's up, Ismail? Nice to see you. Yeah, we're working on the file system today, which is pretty fun. Yeah, moved on past all that other, I don't know, junk with IPC or whatever we were doing in the last like months of this. Now we're on the file system. Right, so name is null terminated, so therefore last element is null terminated, therefore name here is null terminated, and therefore the stir copy will be null terminated. So that's how creating a file works. We just walk it and then copy it in. File open is pretty much just walking it's just forwarding it to walk path. File read, man, how many more? There's like so much stuff here. Okay. File read n bytes. It looks like a lot what am used to do. Wait, awesome stuff. It looks like a lot what am used to do. I don't understand. Like what did you used to do that? Yeah. What's up, Wilson? Thanks a lot for joining. I found your channel work mainly with Java and Angular, so this kind of coding is a little bit different from what I'm used to. Yeah, different worlds indeed. But yeah, thanks for joining. Yeah. I have not done, I did a little bit of Java once and never have done Angular at all. Yeah, I don't know. It's interesting. It's kind of, this like coding in C is also kind of annoying. And what I'm used to work on at school. That's fun. Yeah. Nice. Yeah, it's kind of a first time for me. C looks way better though than Java, maybe. I think they both have their sharp edges, I guess, or annoyances. Okay, how does file reading it? We pass it a file to read from, a buffer to read into, which is count bytes long. And we want to read from some offset, and read count bytes. It's meant to mimic the standard p read. Return the number of bytes read. Okay, how does this work? So just some basic consistency checking. Offset, if offset's greater than file size, that's an error. Return, or I guess just return 0. Otherwise, we get the minimum amount either between count or the rest of the data in the file as the count to read. Yo, Afnan, what's up? What's up? You still made it in time for a bit more of today. Yeah, thanks for joining. Hope you're doing well. Did you finish your travels? I think you were traveling a little bit in the past couple weeks, right? Okay, so how do we read? So I guess the way this works is we go block by block. So offset governs our start position. We set position based on that. And we iterate while position is less than offset plus count. So maybe just to draw it out, we have the file. So here's like the file. And maybe I will just, here we have a file here and it's in a couple blocks. We have some offset into the file. Let's just like randomly point it right here. An offset, and then we have a buffer we're trying to read into, and we are reading count bytes long, and then so we have this position pointer, and I don't really know, like some notion of like position is going to bump along here until we max out offset plus count. So position cannot exceed basically like this. Imagine like a line here, right? Do you have your own IO file implementation or something along the lines of file pointer in the standard library? So I sort of am still trying to understand how it works, but I think yes, there is this struct file type. And I believe that's the rough equivalent of the capital file pointer. Actually, I'm like kind of blanking on how, how these APIs work. It's been a long time since I've used them, but you like what? So there's, I guess there's fopen, but actually that's a user space libc type. This struct file is not a user space type. I think it's actually shared between user space and the kernel, but this is like actually a kernel implementation detail. And I think that's just also used as like the type here. So yeah. So how does this work? So in this loop, I'm gonna just copy it over into the diagram. So we have this loop here, and position starts here at offset, and then we get the block that contains positions. We get this block. I don't know. Or maybe I'll color in. We get this block. No, never mind, I won't do that. So we get this block, and then we read it into memory, and then we locate what? The minimum. This looks complicated. Offset plus count. Offset plus count minus position. It's basically just like how much of the block can we copy, I guess. And because maybe position is all the way up here, for example. And so for example, you know, position could be here. And in that case, we would want to copy this remaining span. So it's like offset plus wait, what? Minus position yields like this number. I'm like kind of confused. Wait, so let me try the other one. Block size minus position. Also what, okay, here's where I don't know the order of precedence, and I might just ask ChatGPT because I don't feel like looking it up. Compute the modulus first, then subtraction. Okay, this is cryptic. What is BN? Yeah. What? Yeah, I'm gonna start with the first one. Block size minus position mod block size. So position is gonna be like at places here. Let's say it's at offset, just like at the start. So the modulus is going to produce this amount. And then it's doing block size minus this amount, which yields the opposite end, right? And so this thing for example, corresponds to this length, at least currently. So basically, wherever position is, it gets the remaining distance to the end of the block, which is kind of like the hard limit of how far we can read. And so maybe to write this, so min hard limit yes, or I think the thing is, what if count is really short and within the block, right? In that case, we don't want to read all the way here. We potentially want to read less than the remaining data in the block. And so to do that, we're trying to find like this certain distance. It's this distance. Hello. It's this distance. And to get this distance, we need like offset okay, right. Position, offset and position are relative to like the start of this thing. So in order to compute this distance, we add it up all the way here and then subtract. So we get this number, which is relative to over here, and subtract position, which is relative to over here, and we get this remaining distance. So basically the goal find out how much we should read from the block, either all the way to the end or less. That's a bit confusing. So we get the actual amount to read. So in the case of the long block that spans, in the case of the long buffer that spans blocks, this thing will resolve to like the rest of the block starting from position, because then we need to go and jump to the next block. And what do? So we compute that length to read, and then we copy it. I guess they use mem move for some reason, which I don't totally understand, but there's buff. What is a block in this context? A block is a file system concept. So the file system breaks up the disk into blocks, and that's kind of the minimum granularity you interact with the disk. Blocks are 4K in length, actually, because there is some kind of interesting integration with the virtual memory subsystem. And so that's like the granularity with which we read and write to the disk. Although technically the disk has its own sector size, which is less than the block size. So the blocks are made up of 8 sectors, but generally it's like this kind of file system chunk amount that we are like interacting with. And we do things in terms of blocks. And so we're going to copy into, wait, how does mem move work again? Destination source, right? So we can copy into buff. What is buff? Buff is the user pointer that we are receiving. And so we're copying in there from a specific place, and that place is, so block points here. Block points here, block plus position. So position mod block size produces this distance from the start of the block, and we just basically compute. We basically convert position from a byte offset relative to the start of the file into a pointer. Because pointer to where that data lives in memory. And so we're copying the data from, so like this argument, these three things corresponds exactly to right here, as a pointer in memory. We copy starting from this region, bn length into the user buffer, and then we update a few variables. So we update, so position now has to be updated based off of how much bn was. So in this case, I think I'll just duplicate this whole thing for the two, maybe for the two cases. So here's the case where it's much smaller, and I'll move this over here. So in this case, here's the bn number. In this case, bn goes all the way. So position needs to get bumped, in either case, to the bn, to the next range of data to read, and here it gets bumped just here. And then here's the next eligible data to read. We also bump buff. Right, so we bump the pointer in the user buffer. Okay. So buff is this pointer. And this, like, if we just read this amount, I'm going to copy just this line, then buff gets bumped to right here, basically. And buff is just kind of like this cursor of where we are writing into the user buffer. And so position and buff get bumped along. And then eventually the loop ends because, okay, I want to kill the palm tree because we're getting close to the end of time. Then eventually position kind of maxes out and reaches the actual end here. And then that's when the loop stops and we return count. Yeah, so in this implementation, it either doesn't return or I see, okay. Actually, I think that's a bug. I actually think it's a bug to return count. Count represents the theoretically desired amount of data to be read, either specified by the caller or determined Yeah, it's like the theoretical amount of data we want to read. However, it's possible that, so count never gets written to. It's not like updated it's not actively keeping track of how much data we were successfully able to read. It's just this kind of like idealized amount of how much we want to read. But if there's disk errors or something, actually, I don't know, if like stuff goes wrong here, then this thing will return R. I see. No, okay, I'm like kind of wrong then. Wait a sec. So if there's an error, we return R, which is less than 0. I see. And so in the case of an error, we just do not return how much data we read, which is like a little bit odd, maybe. So we only return how much data we read if there were no errors. And basically it's either like we can just return the whole thing. There's no intermediate support of like returning only a little bit less. Like we basically always return the amount that they asked for, which is not how it usually works. Usually these implementations can return like arbitrary amounts that are like not what you asked for, like which could be less. So that happened. Okay. Can we, man, there's still all this code. I'm gonna try to speed run reading through the rest of this code. So what if we want to write data? I think it'll be somewhat similar to reading data. Yeah, this core loop is very similar. So we just check, do we need to expand the file? Apparently this just takes care of everything for us. So if we're writing past the end of the currently allocated file size, we need to expand the file, and so this does this. Then we'd have a very, very similar thing where we are kind of tracing. We are, again, tracing along the blocks of the file. But this time, instead of mem moving from the file data into the user buffer, we are mem moving from the user buffer into the data region. But this BN computation is the same. So it's just like the opposite of what we're doing. Rather than kind of tracing along here and copying into count, we trace along and copy from count into here and look up where the block boundaries are. Okay, file, free block, remove a block. So I think it just like deletes a block from the file, which is kind of interesting. So we do a block walk to get, okay, something. Fine, to get the disk block number of a certain file block number. And then pp disk to point. So this is like an output parameter that points to, I'm not sure what. Maybe the bitmap? No. No, it's just the block number. So it's just a pointer to a block number. But what? This is like kind of strange. Find. So that is just simply the output parameter, I guess. Does that mean you can only have one file inside a 4K block? Yes, I believe that is true. So yes, and so the block can only belong to one file, and so if you if you have less than 4K of data, you waste the rest of that block. I believe that's how that works. Yes. And that's just the kind of classic internal fragmentation thing you run into when doing any kind of block-based memory allocation or space allocation. Okay, so whatever. So we look up the block number and we free it. And that's it. Okay. File truncate blocks. This expands or contracts a file. Remove any blocks currently used by file F, but not necessary. Oh. So this kind of trims a file for both the old and new sizes. Figure out the number of blocks required and clear the blocks. So new size, even though it's an offset T, for some reason, this is like the new size we want to truncate it to. And to do that, we're using the free block function to just like free blocks. So what is this? Old blocks. How many blocks are in the file currently? And then how many blocks would be needed for the new file? Starting from new file blocks. Okay, so basically if we made the file smaller, so looping from the end of like the new block size to the old block size, this loop is only going to execute if n blocks was smaller than like if the new n blocks is smaller than the old blocks, meaning we can just get rid of all those extra blocks. And that's what we do. So we just iterate for each of them, freeing these blocks and losing the data. And then next, if n blocks is less than n direct, and we have an indirect pointer, then we can free the indirect. So the indirect is sort of like this optimization kind of thing. So the actual struct file stores some number of pointers to blocks in line in the structure, and then for any other data that overflows past that, the pointers to blocks are stored. Like there's a pointer that points to a block, and that block itself stores pointers to blocks. And so if we trim the file so much that we are now within the range of like the small optimized file, we can completely get rid of all these blocks, and then we can even maybe get rid of this block if we now fit into the first 10 blocks. And that's what this is doing. If n new blocks is less than n direct, which is 10, and we have this pointer here, we free the block, we free this block and set it to 0. Okay, let's just quickly wrap up file set size. We kind of peeked at this a little bit. We have a new size, and if this thing is greater than new size, we truncate away the blocks. We then set the new size. Although what happens if new size is greater? I guess that, wait, does it expand? so far I don't see any expansion happening. So I don't know if this is accurate. Do you see any expansion happening? It just, to me, it looks like it only removes data. So to me, it just seems like it only removes data. But maybe it doesn't, maybe truncating, like resizing the file to be even bigger doesn't require action, because maybe the allocating of new blocks happens here. I don't see that either. Oh, alloc block. Okay, yeah. So it does allocate stuff here if needed. Yes. Okay. Hey Jonathan, what's up? I'm glad you just discovered this channel now. Well, yeah, welcome. Thanks for joining. Yeah, here every week, just doing a bit of programming for fun. Okay, so in order to resize the file, if we make the file smaller, we actually need to like literally free data. But if we're making the file bigger, all we do is just update the size metadata, and we kind of lazily allocate the new data later when we need it and actually write to that. And that makes sense to be efficient. Okay, last two functions, then we'll call it for today. Yeah, it was a bit earlier in the stream, we did a bit more writing code. And then I ran into this part of the lab where it says, like, make sure you read all of the code in this file before you proceed. So that's what I'm doing. File flush. So flushing is when we take the contents, like the disk data that's in memory, and we push it back out to the disk. And let's see, basically we just need to flush every single block, and we do that by looping. We compute the number of blocks in the file plus 1 for like the metadata, the inode block, I guess. Then, okay, we like we call this block walk, and if there's no block or something like that, we just continue. Otherwise we just flush. Otherwise we get a pointer to a block number, which we convert into a disk address, which we then flush using its address. Then we flush the actual file itself. So I don't totally know why it's f size plus block size. Wait, what? F size, the size of the file data, right? Plus block size, but what would that be for? So because the actual metadata, so we have like, so in order to flush a file, we would need to flush this, the struct file, the indirect block if it exists, and any data blocks. And I would kind of think that just f size divided by block size. What's up ASAP? Let's go. Divided by block size would get you the number of blocks, but Okay, I think I know. Wait, so if there's a very small amount of data, like less than a block size, then this, if it was just size divided by block size, that would round down to 0 or get truncated to 0. So we need to at least have one block size to make sure we, just because of like integer division. I see. Okay, so that's why. And then we flush the main block, and then optionally the indirect block if it exists. Lastly, fs sync the entire file system. A big hammer is just go through every single block and flush it. Okay. Whereas this one is only flushing the blocks pertinent to a particular file. This thing just syncs the entire file system. Whew, okay. Well, thanks for kind of bearing with me through that very long and arduous journey through reading and learning how this file system works. With this knowledge, we will be able to continue next week with exercise 4 and beyond. I don't know. We'll see how far we get. But yeah, I think that's going to be it for today. Thanks a lot for joining. This is week 52, so I'm celebrating a year of streaming. And I don't plan on stopping because this is really fun and I'm learning a lot. So yeah, thanks a lot for joining. See you later, Ismail. See you later, John. And I will promote myself. I'll plug my Discord link. 1 year stream. Thanks a lot. What's up, Wilson? See you. This is from OS3 Easy Pieces. Nope, this is from this MIT course. Yeah, all right. Have a great week, everyone. I'll see you later. See you next time. Bye.